This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Fairyland of Science by Arabella Buckley. Read and recorded by Patricia Oakley. Lecture 2. Sunbeams and the Work They Do. Who does not love the sunbeams, and feel brighter and merrier as he watches them playing on the wall, sparkling like diamonds on the ripples of the sea, or making bows of colored light on the waterfall? Is not the sunbeam so dear to us that it has become a household word for all that is merry and gay? And when we want to describe the dearest, busiest little sprite amongst us, who wakes a smile on all faces wherever she goes, do we not call her the sunbeam of the house? And yet, how little even the wisest among us know about the nature and work of these bright messengers of the sun as they dart across space. Did you ever wake quite early in the morning when it was pitch dark and you could see nothing, not even your own hand, and then lie watching as time went on till light came gradually creeping at the window? If you have done this, you will have noticed that you can at first only just distinguish the dim outline of the furniture. Then you can tell the difference between the white cloth on the table and the dark wardrobe beside it. Then by degrees all the smaller details, the handles of the drawer, the pattern on the wall, and the different colors of all the objects in the room become clearer and clearer, till at last you see all distinctly in broad daylight. What has been happening here, and why have the things in the room become visible by such slow degrees? We say that the sun is rising, but we know very well that it is not the sun which moves, but that our earth has been turning slowly round and bringing the little spot on which we live face to face with that great fiery ball, so that his beams can fall upon us. Take a small globe and stick a piece of black plaster over England. Then let a lighted lamp represent the sun, and turn the globe slowly so that the spot creeps round from the dark side away from the lamp until it catches first the rays which pass along the side of the globe, then the more direct rays, and at last stands fully in the blaze of the light. Just this was happening to our spot of the world as you lay in bed and saw the light appear. And we have to learn today what those beams are which fall upon us, and what they do for us. First, we must learn something about the sun itself, since it is the starting place of all the sunbeams. If the sun were a dark mass instead of a fiery one, we should have none of these bright cheering messengers, and though we were turned face to face with him every day, we should remain in one cold eternal night. Now, you will remember we mentioned in the last lecture that it is heat which shakes apart the little atoms of water and makes them float up in the air to fall again as rain, and that if the day is cold they fall as snow, and all the water is turned into ice. But if the sun were altogether dark, think how bitterly cold it would be, far colder than the most wintry weather ever known, because in the bitterest night some warmth comes out of the earth, where it has been stored from the sunlight which fell during the day. But if we never received any warmth at all, no water would ever rise up into the sky, no rain ever fall, no rivers flow, and consequently no plants could grow, and no animals could live. All the water would be in the form of snow and ice, and the earth would be one great frozen mass, with nothing moving upon it. So you see, it becomes very interesting for us to learn what the sun is, and how he sends us his beams. How far away from us do you think he is? On a fine summer's day, when we can see him clearly, it looks as if we had only to get into a balloon and reach him as he sits in the sky. And yet we know roughly that he is more than 91 millions of miles distant from our earth. These figures are so enormous that you cannot really grasp them. But imagine yourself in an express train, traveling at the tremendous rate of 60 miles an hour, and never stopping. At that rate, if you wished to arrive at the sun today, you would have been obliged to start 171 years ago. That is, you must have set off in the early part of the reign of Queen Anne, and you must have gone on never resting through the reigns of George I, George II, and the long reign of George III, then through those of George IV, William IV, and Victoria, whirling on day and night at express speed, and at last today you would have reached the sun. And when you arrived there, how large do you think you would find him to be? Anaxagoras, a learned Greek, was laughed at by all his fellow Greeks because he said that the sun was as large as the Peloponnesus, that is, about the size of Middlesex. How astonished they would have been if they could have known that not only is he bigger than the whole of Greece, but more than 1,000,000 times bigger than the whole world. Our world itself is a very large place, so large that our own country looks only like a tiny speck upon it, and an express train would take nearly a month to travel round it. Yet even our whole globe is nothing in size compared to the sun, for it only measures 8,000 miles across, while the sun measures more than 852,000. Imagine for a moment that you could cut the sun and the earth each in half as you would cut an apple. Then, if you were to lay the flat side of the half earth on the flat side of half the sun, it would take 106 such earths to stretch across the face of the sun. One of these 106 round spots on the diagram represents the size which our earth would look if placed on the sun, and they are so tiny compared to him that they look only like a string of minute beads stretched across his face. Only think, then, how many of these minute dots would be required to fill the whole of the inside if it were a globe. One of the best ways to form an idea of the whole size of the sun is to imagine it to be hollow, like an air ball, and then see how many earths it would take to fill it. You would hardly believe that it would take 1,331,000 globes the size of our world squeezed together. Just think, if a huge giant could travel all over the universe and gather worlds all as big as ours, and were to make first a heap of merely 10 such worlds, how huge it would be. Then he must have 100 such heaps of 10 to make 1,000 worlds. And then he must collect again 1,000 times that 1,000 to make 1,000,000. And when he had stuffed them all into the sunball, he would still have only filled 3/4 of it. After hearing this, you will not be astonished that such a monster should give out an enormous quantity of light and heat, so enormous that it is almost impossible to form any idea of it. Sir John Herschel has, indeed, tried to picture it for us. He found that a ball of lime with a flame of oxygen and hydrogen playing round it, such as we use in magic lanterns and call oxyhydrogen light, becomes so violently hot that it gives the most brilliant artificial light we can get, such that you cannot put your eye near it without injury. Yet if you wanted to have a light as strong as that of our sun, it would not be enough to make such a lime ball as big as the sun is. No, you must make it as big as 146 suns, or more than 146 million times as big as our Earth, in order to get the right amount of light. Then you would have a tolerably good artificial sun, for we know that the body of the sun gives out an intense white light, just as the lime ball does, and that, like it has an atmosphere of glowing gases around it. But perhaps we get the best idea of the mighty heat and light of the sun by remembering how few of the rays which dart out on all sides of this fiery ball can reach our tiny globe, and yet how powerful they are. Look at the globe of a lamp in the middle of a room, and see how its light pours out on all sides and into every corner. Then take a grain of mustard seed, which will very well represent the comparative size of our Earth, and hold it up at a distance from the lamp. How very few of all those rays which are filling the room fall on the little mustard seed, and just so few does our Earth catch of the rays which dart out from the sun. And yet this small quantity, 1/2000 millionth part of the whole, does nearly all the work of our world. In order to see how powerful the sun rays are, you have only to take a magnifying glass and gather them to a point on a piece of brown paper, for they will set the paper alight. Sir John Herschel tells us that at the Cape of Good Hope the heat was even so great that he cooked a beefsteak and roasted some eggs by merely putting them in the sun, in a box with a glass lid. Indeed, just as we should all be frozen to death if the sun were cold, so we should all be burnt up with intolerable heat if his fierce rays fell with all their might upon us. But we have an invisible veil protecting us, made of what do you think? Of those tiny particles of water which the sunbeams draw up and scatter in the air, and which, as we shall see in Lecture 4, cut off part of the intense heat and make the air cool and pleasant for us. We have now learned something of the distance, the size, the light, and the heat of the sun, the great source of the sunbeams. But we are yet no nearer the answer to the question, what is a sunbeam? How does the sun touch our Earth? Now, suppose I wish to touch you from this platform where I stand. I can do it in two ways. Firstly, I can throw something at you and hit you. In this case, a thing will have passed across the space from me to you. Or secondly, if I could make a violent movement so as to shake the floor of the room, you would feel a quivering motion, and so I should touch you across the whole distance of the room. But in this case no thing would have passed from me to you, but a movement or wave which passed along the boards of the floor. Again, if I speak to you, how does the sound reach your ear? Not by anything being thrown from my mouth to your ear, but by the motion of the air. When I speak, I agitate the air near my mouth, and that makes a wave in the air beyond, and that one, another, and another, as we shall see more fully in Lecture 6, till the last wave hits the drum of your ear. Thus, we see there are two ways of touching anything at a distance. First, by throwing something at it and hitting it. Second, by sending a movement or wave across to it, as in the case of the quivering boards and the air. Now the great natural philosopher Newton thought that the sun touched us in the first of these waves, and that sunbeams were made of very minute atoms of matter thrown out by the sun, and making a perpetual cannonade on our eyes. It is easy to understand that this would make us see light and feel heat, just as a blow in the eye makes us see stars, or on the body makes it feel hot, and for a long time this explanation was supposed to be the true one. But we know now that there are many facts which cannot be explained on this theory, though we cannot go into them here. What we will do is to try and understand what now seems to be the true explanation of the sunbeam. About the same time that Newton wrote, a Dutchman named Huygens suggested that light comes from the sun in tiny waves, traveling across space much in the same way as ripples travel across a pond. The only difficulty was to explain in what substance these waves could be traveling, not through water, for we know that there is no water in space, nor through air, for the air stops at a comparatively short distance from our earth. There must be something filling all space between us and the sun, finer than either water or air. And now I must ask you to use all your imagination, for I want you to picture to yourselves something quite as invisible as the Emperor's new clothes in Andersen's fairy tale, only with this difference, that our invisible something is very active, and though we can neither see it nor touch it, we know it by its effects. You must imagine a fine substance filling all space between us and the sun and the stars, a substance so very delicate and subtle that not only is it invisible, but it can pass through solid bodies such as glass, ice, or even wood or brick walls. This substance we call ether. I cannot give you here the reasons why we must assume that it is throughout all space. You must take this on the word of such men as Sir John Herschel or Professor Clerk Maxwell until you can study the question for yourselves. Now, if you can imagine this ether filling every corner of space, so that it is everywhere and passes through everything, ask yourselves what must happen when a great commotion is going on in one of the large bodies which float in it. When the atoms of the gases round the sun are clashing violently together to make all its light and heat, do you not think they must shake this ether all around them? And then, since the ether stretches on all sides of the sun to our earth and all other planets, must not this quivering travel to us, just as the quivering of the boards would from me to you? Take a basin of water to represent the ether, and take a piece of potassium, like that which we used in our last lecture, and hold it with a pair of nippers in the middle of the water. You will see that as the potassium hisses and the flame burns round it, they will make waves which will travel all over the water to the edge of the basin, and you can imagine how in the same way waves travel over the ether from the sun to us. Straight away from the sun on all sides, never stopping, never resting, but chasing after each other with marvelous quickness, these tiny waves travel out into space by night and by day. When our spot of the earth, where England lies, is turned away from them, and they cannot touch us, then it is night for us. But directly England is turned so as to face the sun, then they strike on the land and the water, and warm it, or upon our eyes, making the nerves quiver so that we see light. Look up at the sun and picture to yourself that instead of one great blow from a fist causing you to see stars for a moment, millions of tiny blows from these sun waves are striking every instant on your eye. Then you will easily understand that this would cause you to see a constant blaze of light. But when the sun is away, if the night is clear, we have light from the stars. Do these then too make waves all across the enormous distance between them and us? Certainly they do, for they too are suns like our own, only they are so far off that the waves they send are more feeble, and so we only notice them when the sun's stronger waves are away. But perhaps you will ask, if no one has ever seen these waves, nor the ether in which they are made, what right have we to say they are there? Strange as it may seem, though we cannot see them, we have measured them, and know how large they are, and how many can go into an inch of space. For as these tiny waves are running on straight forward through the room, if we put something in their way, they will have to run around it, and if you let in a very narrow ray of light through a shutter and put an upright wire in the sunbeam, you actually make the waves run round the wire, just as water runs round a post in a river, and they meet behind the wire just as the water meets in a V shape behind the post. Now, when they meet, they run up against each other, and here it is we can catch them. For if they meet comfortably, both rising up in a good wave, they run on together and make a bright line of light. But if they meet higgledy-piggledy, one up and the other down, all in confusion, they stop each other, and then there is no light, but a line of darkness. And so, behind your piece of wire, you can catch the waves on a piece of paper, and you will find that they make dark and light lines, one side by side with the other, and by means of these bands it is possible to find out how large the waves must be. This question is too difficult for us to work it out here, but you can see that large waves will make broader light and dark bands than small ones will, and that in this way the size of the waves may be measured. And now, how large do you think they turn out to be? So very, very tiny that about 50,000 waves are contained in a single inch of space. I have drawn on the board the length of an inch. Now I will measure the same space in the air between my finger and my thumb. Within this space, at this moment, there are 50,000 tiny waves moving up and down. I promised you we will find in science things as wonderful as in fairy tales. Are not these tiny invisible messengers coming incessantly from the sun as wonderful as any fairies? And still more so when, as we shall see presently, they are doing nearly all the work of our world. You must next try to realize how fast these waves travel. You will remember that an express train will take 171 years to reach us from the sun, and even a cannonball would take from 10 to 13 years to come that distance. Well, these tiny waves take only 7 minutes and a half to come the whole 91 millions of miles. The waves which are hitting your eye at this moment are caused by a movement which began at the sun only 7.5 minutes ago. And remember, this movement is going on incessantly, and these waves are always following one after the other so rapidly that they keep up a perpetual cannonade upon the pupil of your eye. So fast do they come that about 608 billion waves enter your eye in one single second. I do not ask you to remember these figures. I only ask you to try and picture to yourselves these infinitely tiny and active invisible messengers from the sun, and to acknowledge that light is a fairy thing. But we do not yet know all about our sunbeams. See, I have here a piece of glass with 3 sides, called a prism. If I put it in the sunlight, which is streaming through the window, what happens? Look, on the table there is a line of beautiful colors. I can make it long or short as I turn the prism, but the colors always remain arranged in the same way. Here at my left hand is red, beyond it orange, then yellow, green, blue, indigo or deep blue, and violet, shading one into the other all along the line. We have all seen these colors dancing on the wall when the sun has been shining brightly on the cut glass pendants of the chandelier, and you may see them still more distinctly if you let a ray of light into a darkened room and pass it through the prism. What are these colors? Do they come from the glass? No, for you will remember to have seen them in the rainbow, and in the soap bubble, and even in a drop of dew on the scum on the top of a pond. This beautiful colored line is only our sunbeam again, which has been split up into many colors by passing through the glass, as it is in the raindrops of the rainbow and the bubbles of the scum of the pond. Till now we have talked of the sunbeam as if it were made of only one set of waves, but in truth it is made of many sets of waves of different sizes, all traveling along together from the sun. These various waves have been measured, and we know that the waves which make up the red light are larger and more lazy than those which make violet light, and that there are only 39,000 red waves in an inch, while there are 57,000 violet waves in the same space. How is it, then, that if all these different waves making different colors hit on our eye, they do not always make us see colored light? Because, unless they are interfered with, they all travel along together, and you know that all colors mixed together in proper proportions makes white. I have here a round piece of cardboard, painted with the 7 colors in succession several times over. When it is still, you can distinguish them all apart, but when I whirl it quickly around, see, the cardboard looks quite white, because we see them all so instantaneously that they are mingled together. In the same way, light looks white to you because all the different colored waves strike on your eye at once. You can easily make one of these cards for yourselves, only the white will look dirty because you cannot get the colors pure. Now, when the light passes through the 3-sided glass or prism, the waves are spread out, and the slow, heavy red waves lag behind and remain at the lower end of the colored line on the wall, while the rapid little violet waves are bent more out of their road and run to the farther end of the line, and the orange, yellow, green, blue, and indigo arrange themselves between according to the size of their waves. And now you are very likely eager to ask why the quick waves should make us see one color and the slow waves another. This is a very difficult question, for we have a great deal still to learn about the effect of light on the eye. But you can easily imagine that color is to our eye much the same as music is to our ear. You know we can distinguish different notes when the air waves play slowly or quickly upon the drum of the ear, as we shall see in Lecture 6. And somewhat in the same way, the tiny waves of the ether play on the retina or curtain at the back of our eye, and make the nerves carry different messages to the brain, and the color we see depends upon the number of waves which play upon the retina in a second. Do you think we have now rightly answered the question, what is a sunbeam? We have seen that it is really a succession of tiny rapid waves, traveling from the sun to us across the invisible substance we call ether, and keeping up a constant cannonade upon everything which comes in their way. We have also seen that, tiny as these waves are, they can still vary in size, so that one single sunbeam is made up of myriads of different sized waves, which travel all together and make us see white light, unless for some reason they are scattered apart, so that we see them separately as red, green, blue, or yellow. How they are scattered, and many other secrets of the sun waves, we cannot stop to consider now, but we must pass on to ask, what work do the sunbeams do for us? They do two things. They give us light and heat. It is by means of them alone that we see anything. When the room was dark, you could not distinguish the table, the chairs, or even the walls of the room. Why? Because they had no light waves to send to your eye. But as the sunbeams began to pour in at the window, the waves played upon the things in the room, and when they hit them, they bounded off them back to your eye, as a wave of the sea bounds back from a rock and strikes against a passing boat. Then, when they fell upon your eye, they entered it and exited the retina and the nerves, and the image of the chair or the table was carried to your brain. Look around at all the things in this room. Is it not strange to think that each one of them is sending these invisible messengers straight to your eye as you look at it, and that you see me and distinguish me from the table entirely by the kinds of waves we each send to you? Some substances send back hardly any waves of light, but let them all pass through them, and thus we cannot see them. A pane of clear glass, for instance, lets nearly all the light waves pass through it, and therefore you often cannot see that the glass is there, because no light messengers come back to you from it. Thus people have sometimes walked up against a glass door and broken it, not seeing it was there. Those substances are transparent, which, for some reason unknown to us, allow the ether waves to pass through them without shaking the atoms of which the substance is made. In clear glass, for example, all the light waves pass through without affecting the substance of the glass, while in a white wall the larger part of the rays are reflected back to your eye, and those which pass into the wall by giving motion to its atoms lose their own vibrations. Into polished shining metal the waves hardly enter at all, but are thrown back from the surface, and so a steel knife or a silver spoon are very bright and are clearly seen. Quicksilver is put at the back of the looking glasses because it reflects so many waves. It not only sends back those which come from the sun, but those too which come from your face. So when you see yourself in a looking glass, the sun waves have first played on your face and bounded off from it to the looking glass. Then, when they strike the looking glass, they are thrown back again onto the retina of your eye, and you see your own face, by means of the very waves you threw off from it an instant before. But the reflected light waves do more for us than this. They not only make us see things, but they make us see them in different colors. What, you will ask, is this too the work of the sunbeams? Certainly, for if the color we see depends on the size of the waves which come back to us, then we must see things colored differently according to the waves they send back. For instance, imagine a sunbeam playing on a leaf. Part of its waves bound straight back from it to our eye, and make us see the surface of the leaf, but the rest go right into the leaf itself, and there are some of them that are used up and kept prisoners. The red, orange, yellow, blue, and violet waves are all useful to the leaf, and it does not let them go again. But it cannot absorb the green waves, and so it throws them back, and they travel to your eye and make you see a green color. So when you say a leaf is green, you mean that the leaf does not want the green waves of the sunbeam, but sends them back to you. In the same way, the scarlet geranium rejects the red waves, and this table sends back brown waves. A white tablecloth sends back nearly all the whole of the waves, and a black coat scarcely any. This is why, when there is very little light in the room, you can see a white tablecloth while you would not be able to distinguish a black object, because the few faint rays that are there are all sent back to you from a white surface. Is it not curious to think that there is really no such thing as color in the leaf, the table, the coat, or the geranium flower, but we see them of different colors because, for some reason, they send back only certain colored waves to our eye? Wherever you look, then, and whatever you see, all the beautiful tints, colors, lights, and shades around you are the work of the tiny sun waves. Again, light does a great deal of work when it falls upon plants. Those rays of light which are caught by the leaf are by no means idle. We shall see in Lecture 7 that the leaf uses them to digest its food and make the sap on which the plant feeds. We all know that a plant becomes pale and sickly if it has not sunlight, and the reason is that without these light waves it cannot get food out of the air, nor make the sap and juices which it needs. When you look at plants and trees growing in the beautiful meadows, at the fields of corn, and at the lovely landscape, you are looking on the work of tiny waves of light, which never rest all through the day in helping to give life to every green thing that grows. So far we have spoken only of light, but hold your hand in the sun and feel the heat of the sunbeams, and then consider if the waves of heat do not do work also. There are many waves in a sunbeam which move too slowly to make us see light when they hit our eye, but we can feel them as heat, though we cannot see them as light. The simplest way of feeling heat waves is to hold a warm iron near your face. You know that no light comes from it, yet you can feel the heat waves beating violently against your face and scorching it. Now, there are many of these dark heat rays in a sunbeam, and it is they which do most of the work in the world. In the first place, as they come quivering to the earth, it is they which shake the water drops apart, so that these are carried up into the air, as we shall see in the next lecture. And then remember, it is these drops falling again as rain which make the rivers and all the moving water on the earth. So also it is the heat waves which make the air hot and light, and so cause it to rise and make winds and air currents, and these again give rise to ocean currents. It is these dark rays again which strike upon land and give it warmth, which enables plants to grow. It is they also which keep up the warmth in our own bodies, both by coming to us directly from the sun, and also in a very roundabout way through plants. You will remember that plants use up rays of light and heat in growing. Then either we eat the plants, or animals eat the plants and we eat the animals. And when we digest the food, that heat comes back in our bodies, which the plants first took from the sunbeams. Breathe upon your hand and feel how hot your breath is. Well, that heat which you feel was once in a sunbeam, and has traveled from it through the food which you have eaten, and has now been at work keeping up the heat of your body. But there is another way in which these plants may give out the heat waves they have imprisoned. You will remember how we learned in the first lecture that coal is made of plants, and that the heat they give out is the heat these plants once took in. Think how much work is done by burning coals. Not only are our houses warmed by coal fires and lighted by coal gas, but our steam engines and machinery work entirely by water which has been turned into steam by the heat of coal and coke fires. And our steamboats travel all over the world by means of the same power. In the same way, the oil of our lamps comes either from olives which grow on trees, or from coal and the remains of plants and animals in the earth. Even our tallow candles are made from mutton fat, and sheep eat grass, and so turn which way we will, we find that the light and heat on our earth, whether it comes from fires or candles or lamps or gas, and whether it moves machinery or drives a train or propels a ship, is equally the work of the invisible waves of ether coming from the sun, which make what we call a sunbeam. Lastly, there are still some hidden waves which we have not yet mentioned, which are not useful to us either as light or heat, and yet they are not idle. Before I began this lecture, I put a piece of paper which had been dipped in nitrate of silver under a piece of glass, and between it and the glass I put a piece of lace. Look what the sun has been doing while I have been speaking. It has been breaking up the nitrate of silver on the paper and turning it into a deep brown substance. Only where the threads of the white lace were, and the sun could not touch the nitrate of silver, there the paper has remained light-colored, and by this means I have a beautiful impression of the lace on the paper. I will now dip the impression into water, in which some hydrosulfite of soda is dissolved, and this will fix the picture. That is, prevent the sun acting upon it any more. Then the picture will remain distinct, and I can pass it round to you all. Here again, invisible waves have been at work, and this time neither as light nor as heat, but as chemical agents. And it is these waves which give us all our beautiful photographs. In any toy shop you can buy this prepared paper and set the chemical waves at work to make pictures. Only you must remember to fix it in the solution afterwards. Otherwise the chemical rays will go on working after you have taken the lace away, and the paper will become brown and your picture will disappear. And now tell me, may we not honestly say that the invisible waves which make our sunbeams are wonderful fairy messengers as they travel eternally and unceasingly across space, never resting, never tiring in doing the work of our world? Little as we have been able to learn about them in one short hour, do they not seem to you worth studying and worth thinking about as we look at the beautiful results of their work? The ancient Greeks worshipped the sun and condemned to death one of their greatest philosophers, named Anaxagoras, because he denied that it was a god. We can scarcely wonder at this when we see what the sun does for our world, but we know that it is a huge globe made of gases and fiery matter, and not a god. We are grateful for the sun instead of to him, and surely we shall look at him with new interest now that we can picture his tiny messengers, the sunbeams, flitting all over space, falling upon our earth, giving us light to see with and beautiful colors to enjoy, warming the air and the earth, making the refreshing rain, and, in a word, filling the world with life and gladness. End of Lecture 2. This recording is in the public domain.